Hey guys, what's up? Today we are going to finish out the metric tensor discussion and have our quiz. Maybe next time we will look at a worksheet for chapter 5. So we'll see what's up. But any questions before we get started? Hey guys, what's up? Today we are going to finish. We'll see. Any questions before? Sean, do you mean like on Moodle or do you mean in your folder? That's strange. I don't know. I have to double check that. That's weird. I had those up earlier this week, so I'm not sure why it's not showing up for you yet. I'll double check on that when we get done. Okay, I'll double check. Okay, let's get started. Just to kind of recap a little bit what we talked about last time. So last time we went through, had a little discussion again about the covariant basis CI down, and that was partial R, partial XI, and then GIJ was defined as ZI down dotted with ZJ down. And so that was our definition of the metric tensor. And the metric tensor allows us to calculate arc length. And so it's square root of GIJ dxi dt dxj dt. So that's our discussion from last time, more or less. I mean, we showed a few things, but yeah, that was kind of the main things that we talked about last time, were the covariant basis again, the metric tensor, and then arc length. So it's the covariant basis, metric tensor, and arc length. And again, the metric tensor tells us how to calculate the length or the distance between points in some space or some surface. So I'm going to continue our discussion a little bit today about the metric tensor. We showed at the end of class last time that the metric tensor is indeed a 0-2 tensor. Yeah, I'll double check. I'll go ahead and start posting everything on Moodle if it's not on there already. I thought I had done that, but maybe I was looking at a different class, and I'll double check. But I'll start putting stuff on Moodle. So today the theorem we're going to start with is that if the Jacobian matrix of a transformation from xi to rectangular coordinates call it xi prime is some Jacobian matrix J equal to partial xi prime partial x. We'll call it J R or something like that, doesn't matter. So differentiating the rectangular coordinates with respect to the non-rectangular coordinates to get the Jacobian. If that Jacobian is capital J, then the metric is given by Gij in matrix form can be written as J transpose times J. Which is a tensor whose components are in the xi system. For example, say x equals r cosine theta and y equals r sine theta. Then J would be the matrix. Differentiate x1 prime, which is x, x1 prime, x2 prime, x1, x2. So differentiate x with respect to r, you get cosine theta. And differentiate x with respect to theta, you get negative r sine theta. Down here you get sine theta, here you get r cosine theta. J transpose is equal to cosine theta sine theta, negative r sine theta, r cosine theta. And then J transpose J be equal to cosine theta sine theta, negative r sine theta, r cosine theta times cosine theta, negative r sine theta, r cosine theta. And that matrix multiplication comes out to be cosine squared plus sine squared, and then negative r sine theta cosine theta plus r sine theta cosine theta. And then down here get negative r sine theta cosine theta plus r sine theta cosine theta. And then here we get r squared sine squared plus r squared cosine squared, which is 1, 0, 0 r squared, which is the metric for polar, or metric for 2D flat space in polar coordinates. Like we discussed last time. So that is our verification, I guess, of the theorem, you could say. This is the flat space metric for 2 dimensions represented in polar coordinates. So if you have your transformation that goes from basically if you have x, y, and z, or x and y in terms of your other coordinates, you can calculate the metric a little more quickly than doing the position vector stuff in the covariant basis approach. So it's pretty nice. Of course, that's if you have it in Cartesian, or if you have like the Cartesian transformation equations, basically. All right, let's look at one more example here today. The example says calculate in Cartesian and cylindrical. So let's look at the length of a helix. Okay, example, calculate in Cartesian and cylindrical. Oh, any questions about the example? Okay. Another example here says find the arc length using A, Cartesian coordinates, and B, cylindrical coordinates. So find the arc length of a curve C, which is x equals 2 cosine t, y equals 2 sine t, z equals 4t. So this is the helix in R3. And t is going from 0 to 2 pi. So we're going to find the arc length of this curve using cylindrical and Cartesian coordinates. So solution. The first one, in Cartesian coordinates, we have the metric Gij is actually delta ij down. So Gij dxi dt dxj dt, call this x1, x2, and x3. This would just be dx dt squared plus dy dt squared plus dz dt squared, which would be, let's see, 4 sine squared t plus 4 cosine squared t plus 16, sorry, plus 16. So this is going to be s equals the integral from 0 to 2 pi square root of basically 4, this is just 4 plus 16, so square root of 20 dt, which is 2 pi square root of 20. Now it would be the arc length of the curve. Part B, Gij is equal to 1, 0, 0, or sorry, it's three-dimensional. So 1, 0, 0, 0, r squared, 0, 0, 0, 1. But now our coordinates are r equals 2, theta equals t, and z equals 4t. So now our coordinates x1, x2, x3 look like this. Because it's a circle of radius 2, I just fix r to be 2. T is my angle, theta, and then z is 4t. So now gij dxi dt dxj dt equal to 1 times dr dt squared plus r squared times d theta dt squared plus 1 times dz dt squared. Which will be 1 times 0 plus r squared times 1 plus 1 times 4. So, but what is r? Here, r is 2. So this is actually equal to 4 plus 4, which is 8. Whoops, sorry, forgot my square there. So 4 plus 4, which is 16. 20. So then the arc length s is equal to the integral from 0 to 2 pi square root of 20 dt, which is again 2 pi square root of 20. So the arc length is the same regardless of which coordinate system I use to calculate it. Of course, if I change my coordinate system, I have to change my metric tensor representation. Which one do you mean? Sorry. All right, cool. Let's see, are there any other questions? Okay, cool. I guess we'll just call it a day. I'll switch over to the Zoom meeting. We may start the quiz a little early so that you don't have to go too far past 3 o'clock, if that's cool. But yeah, let's just go ahead and do the quiz, and we'll switch over to the Zoom meeting. So